the participants. Let me know if my slide screen is visible. The screen visible?
Yes, sir. Perfect.
So, good morning, everyone. Today, we'll be seeing there is a term named blockchain technology, and we have heard so many things about this blockchain. It has so much of potential, and it is useful in almost all the application areas, especially in the field of smart cities and all. And this blockchain is for preserving data. So today in this 1 hour lecture, I will only discuss what this term actually means. What do we mean by this blockchain technology and how this is useful for preserving data? So we'll be seeing the formal definitions of blockchain and how this blockchain is different from traditional database. Then sometimes we get confused. We say blockchain is a database. So is it a database? And if it is, how is it different from the traditional database? So these things we'll be seeing today. And then moving on to, we'll see seeing the transaction process life cycle of blockchain. We all have heard about Bitcoin, isn't it? So I'll be taking the example of Bitcoin and understand how this process life cycle of blockchain is actually executed. Moving on to the architecture and classification of blockchain technology, and if time permits, we will also be seeing the problems in IoT, some blockchain-based IoT applications, and finally we'll conclude the need for blockchain in terms of data privacy. So these are the topics that we'll be seeing today. And the first and the foremost, what actually is a blockchain? If we are from engineering background, not only computer science, any engineering background, we might have heard something called a linked list. Even if you are very much new to this blockchain, you might have heard something called linked list. It is nothing but a data structure, and we have nodes in a linked list, and these nodes are linked to each other. Blockchain also have nodes. They are also linked to each other. Only thing is that in the linked list we have, hello. Actually, I'll call you in an hour, okay? Yeah. So we have, sorry for the interruption. So blockchain is nothing but a type of linked list where the linking is not done on the basis of memory addresses. So we have some other type of linking. We call that linking to be a hash linking. So at this point of time, in this slide, I am not discussing what that linking will be. Only thing is that it is not based on the memory addresses. It is something else. So we imagine this blockchain to be a series of blocks, like series of nodes, and all the blocks are connected to the previous block by some kind of a link. We call it a distributed data structure. So this is a formal definition of blockchain, and there are four important terms here. So first of all, let me read this definition for you. Blockchain is a decentralized computation and information sharing platform. Now, we say if it is a platform, it is not a database. So blockchain is a decentralized computation information sharing platform that enables multiple authoritative domains or peers who don't trust each other. Why don't they trust each other? To cooperate, coordinate, collaborate in a rational decision making process. So if there are several domains, several people who don't trust each other, however they need to reach some kind of rational decision making process, they need a platform. That platform should be decentralized. This decentralized platform is a blockchain. This is a formal definition. Now here I have highlighted four things in red: decentralized, information sharing platform, multiple authoritative domains, rational decision making process. In order to understand this definition clearly, we will be seeing all these four terms one by one in more detail before we arrive to the formal definition of blockchain. First term, decentralized architecture. So what do we mean by decentralization? Initially, we had centralized architecture where we had a central coordination system, and this coordination system used to give orders to all the peers. Like, for example, one single system was there that actually coordinates all the other nodes attached to them. Then what happens? The problem here in the centralized architecture, it is a master slave architecture basically. And so what happens? All the nodes will lose connection in the central server phase. If the server central system that is actually coordinating, that is the master system, if that system fails, all the other nodes will not receive orders from anyone. So all the nodes will lose connection because they are dependent on one single system. This is called single point of failure. So what happens? We move to the decentralized architecture where instead of having one central master, one central node, we have several of the coordinator nodes. And these individual nodes connect to these coordinator nodes to receive order. And if suppose some coordinator nodes fail, what will happen? The nodes of that particular failed coordinator nodes, they can join some other coordinator nodes, and so on and so forth. So what happens? This single point of failure problem is overcome. So this works. So this decentralized architecture can work even under some number of failures. So this is a decentralized architecture. So I have a look at the centralized decentralized architecture first. So all the nodes are connected to a single authority in the centralized network. The first diagram you can see. In the second one, you can see the nodes are connected to some coordinator nodes. We have 6 coordinator nodes, and this is a decentralized network where no single authority or server control the node. Now, what blockchain uses? That we use the term decentralized, but actually it is not a decentralized network. Blockchain uses a distributed type of network, that is nothing but the enhanced version of the decentralized network that we know. So every node is independent and they are connected to each other. So just the decentralized network, if you connect all the nodes with each other, it will be a distributed network. So this is how actually a blockchain is called a distributed network. The second term that we had seen in the definition was information sharing platform. So what do you mean by information sharing platform? How did we initially share information? So participants, anybody can tell me how did we initially share information? Any idea?
Sir, so sorry, like the participants are all muted,
Okay,
so
okay, okay,
we could
good.
not respond.
Okay, thank you. So initially we had Microsoft Word. Suppose two persons, that is Bharat and Bharti. They are working on a project, on a common project. So how will they share information? Initially we had this MS Word. So Bharat will write some document, he will send it to Bharti, and Bharti will edit in that particular document, send back to Bharat, and so on and so forth. So this will continue and the project will be complete. What is the problem? What are the disadvantages? Bharat and Bharti is not able to simultaneously edit the document. When Bharat is working, Bharti will not be able to work on that document. And when Bharti is working, Bharat will not be able to work on that particular document. So both are not able to simultaneously edit the same document, simultaneously work on the same project. Next, shared Google Doc. What it allows? It allows both Bharat and Bharti a centralized environment where both can work on the document together. The shared Google Doc is editable by both the users. Don't confuse the Microsoft Word and shared Google Doc. This is only example that supports that definition of blockchain. Blockchain is not at all a Word file or a shared Google Doc. This example will support the definition of blockchain. So here in shared Google Doc, both can edit the document together, work on the document together. However, again, the problem here is this is susceptible to single point of failure. So what the blockchain have, an ideal solution where Bharat have his own copy, Bharti has her own copy. And both Bharat and Bharti can independently write their own personal copy. Bharat can edit in his copy, Bharti can edit in her copy. And whatever they are editing, that change will be reflected in one single central copy on the central cloud. So blockchain ensures that whatever is written by both is getting synchronized with each other, and both will be able to see the most updated copy. So this central cloud enables, this blockchain actually enables both these persons to see the most updated copy. Now both can simultaneously read and write the document. The first problem is solved. Second, even if the central cloud is failed, central server fails, what happens? Both Bharat and Bharti has the most updated copy of the document. So there is no loss of information also. So both can simultaneously work on the document, and also there is no loss of information. Third thing that we had seen was multiple authoritative domains. So here we can say there are so many nodes, there are so many peers, and none of the nodes, none of the peers actually trust each other. So every node will maintain a local copy of the global data set. So what happens? There is a global data set, the global information, global seat, you can say. Every node has a local copy of that particular, and the database of this historical information that is available to everyone, we call this a public ledger. What does this mean? Suppose node 1 makes some transaction. Suppose node 1 sends some amount to node 6. This all the users. So this is how in the local copy of all the users. So in order to ensure consistency, the local copies at every node is identical, and these local copies are also updated on the basis of the global information. So suppose node 2 has sent some amount to node 3, this information will be uploaded in the public ledger, and this will also be available to node 5, node 6, node 4, and all the nodes in the network. So this is how multiple authoritative domains trust each other in order to make a rational decision making. Last term in the definition was a rational decision making process. So what do we mean by rational decision? It is nothing but correct decision. Let's have a look at this rational decision making process with the help of an example. Suppose there are four friends in a network: Bharat, Bharti, Vector, and Eve. So all Bharat is having $100 in his account, and he puts in the public ledger that I have $100 with him. Now this information will be available to all the four users. What is this rectangle here? This rectangle here is the local copy. This Bharat, Bharti, Vector, and Neve are the nodes. This rectangle is the local copy of all the nodes. All the nodes have their local copy, and public ledger is not seen. So everyone knows that Bharat is having $100 with him. Now Bharat wants to send it to Bharti. So suppose Bharat is allowed to send $50 to Bharti. Now, each and every person in this network reaches or allows or permits Bharat to do some kind of transaction. Sending $50 to Bharti is called a transaction, and this transaction is first reflected in somewhere in the public ledger, and this is reflected in the local copy. So when Bharat is allowed to send $50 to Bharti, therefore this is reflected in the local copy of all these. Now, now Bharti also wants to send $30 to Eve. Everyone in the network knows that now Bharat is having $50. Bharti is also having $50 because Bharat has already given $50 to Bharti. Now Bharti wants to send $30 to Eve. Everyone knows Bharti is capable. She has $50 with her, so she can send it to Eve. So everyone allows, and this $30 transaction is also reflected in the local copy of all. Now, Bharat makes a new request. Now, just understand how this transaction. First, someone makes a request, everyone agrees to this, and then only this is reflected in the local copy. So, Bharat puts on a new request that I want to send $80 to Vector. Now, This request is validated by all the users validate this, all the users jointly reach to a conclusion, all the users reach to a consensus. We have a very important term called consensus when every user reaches to a common conclusion. We will see that in detail. So Bharat wants to send $80 to Vector. What will happen? Bharat is having only $50, and everyone knows that Bharat is not able to, he does not have the capacity to send $80 to Vector. So this transaction will be denied. And we all know that a denied transaction is never updated in the local copy. So if the transaction is denied, it will not be updated. So this is how actually we reach to a rational or correct decision making. So the data here is replicated all over, and this again gives us some kind of advantage in terms of data integrity. Also, the consensus is maintained. Consistency is maintained with the help of consensus. As I said, consensus means that everyone agrees that the data that goes into the data structure is what they agree to put there. When everyone agrees, then only that particular data will be entered. And for linking, there is a cryptographic technique called hash link. Now don't confuse that these are the nodes in a blockchain. These are the transactions. We'll see how these transactions are bundled into nodes and how the link nodes are connected using a hash link. So this is the formal definition of blockchain. We arrived that a blockchain is an open distributed ledger that can record transactions between two parties efficiently and in a verifiable and permanent manner. So these are some of the terms related to the formal definition of blockchain. How is it different from a traditional centralized architecture? In the normal centralized architecture figure A, you can see user suppose wants to access some data. So what will happen? It will first send a request. So user is sending a request, can I access data X? And the centralized server, it sends a response, okay, based on the permissions, based on the privileges assigned to the user, centralized server response makes a response to the user. So this is how normal centralized architecture functions, operates. In case of blockchain network, what do we have? The user makes a request, can I access data X? Okay. Now, all these nodes, all these peers in the network will reach to a common decision, a common conclusion. That is called a consensus response. Everyone will agree to a response. So blockchain architecture gives a consensus response in opposition to the centralized architecture of the traditional database. So we have centralized data storage in traditional database. Here we have decentralized storage. There is a need for database admin. There is no need for an administrator in a blockchain. Further, modifying data requires permission from database admin. The administrator needs to give permission in order to, if somebody wants to modify any data. Here in the blockchain, what happens? Nobody needs any permission. If you want to modify it, but it will be reflected in the public ledger only if everyone agrees to this particular thing. So user have a copy of data and he can modify the copy. However, this modification will not affect the master copy of the data. And this will be affected only when all the other users actually agree on this particular modification. Further, this centralized database keep information that is up to date. However, blockchain will keep information, all the information throughout. And then centralized database are used as databases. However, blockchains is a transaction platform, ideal for transaction platform. We don't often use it as a database. So this is moving on to the blockchain transaction process lifecycle. So I'll take an example of a Bitcoin. How a Bitcoin amount is credited in from one account to another. How do we send Bitcoins from one account to another? So we'll see this stepwise. First, suppose Alice wants to send some amount to Bob. So what will happen? In step one, you can see Alice will open her Bitcoin wallet. First of all, she needs to open the wallet. Good. Step one. Step two. Once you open the wallet, what will you do? You will do two things. You will give the address of the sender or address to whom you want to send the amount and the amount that you want to transfer. So you will provide the address of the Bob and what amount you want to transfer. Once you provide the address and amount to be transferred, you click on the send button. What does this clicking on send button means? This clicking on send button means this thing. This Bharat is making a request of sending $80 to Vector. This is the meaning of clicking on send button. So once the send command is given, the wallet will construct a transaction digitally signed using its private key. We'll see the concept of private key and digital signatures, and it is broadcasted to the network. So the transaction is constructed and it is broadcasted to the network. Why is it broadcasted? So that all the other network nodes validate the transaction. How? Based on the existing blockchain, and they propagate the transaction to the miners. So if all the nodes have validated and have checked the authenticity of this particular transaction, this transaction is sent to the miner. So once this transaction is given to the miner, is nothing but some specialized nodes that actually attach this transaction to the blockchain. So miners include the transaction to the next block to be mined. So we have a blockchain. In this chain, we are attaching some blocks, and these blocks are consisting of several transactions. What the miners will do? Miner will take the transaction, put it into block. Miner will again take some transaction, put it into block, and this particular block will be added to the blockchain after some stage. So miners include the transaction to the next block to be mined. Now, what does they do? The miners collect all the transactions. There will be several transactions of this type. So miners will collect all the transactions, create a new block, or add these transactions to some kind of existing block and perform mining. Means adding this block to the existing blockchain. So it tries to connect it with existing blockchain. And how do we connect? With the help of cryptographic hash function, hash linking or hashing technique. So it is added to the existing blockchain. And once the mining is over, block is included in the existing blockchain, the updated ledger is propagated throughout the network. And once the updated ledger is propagated, the local copy of all these just get modified. So after this, the Bob will open his Bitcoin wallet. The blockchain gets updated because the public ledger is updated. The transaction will be reflected at the Bob's wallet. So let's have a look at this pictorially. Initially, the transaction is requested. So transaction request is made here. It is broadcasted to the network. The requested transaction is broadcasted to the peer-to-peer network that consists of several users called nodes. So all these four nodes will receive this transaction. So what does the nodes do? They validate the transaction. So transaction is validated by the network of nodes. So all the four nodes have validated this particular transaction, and this validated transaction can be a cryptocurrency, contract, record, or any other information for that matter. And these verified transactions are combined with other transactions. So there will be some previous transactions, there is some new transactions. All these transactions are bundled in the form of a block. And this block is then added to the existing blockchain. So newly created block is added to the existing chain of blocks, and the transaction is completed after the public ledger is updated. So this is the same thing. Transaction initiated, transaction is broadcasted to the network, miners verify the transaction, bundle them into blocks, and very importantly, who will, if once the block is made, who will actually attach this block to the existing blockchain? Here we have a concept of cryptographic puzzle. The miners race towards solving a cryptographic puzzle, and someone who wins this particular race, or those who solve this cryptographic puzzle first, will be allowed to mine this block. Mining a block means they will also receive some kind of incentive for this. So I'm not going into the details of that at this very point. So winner will add the block to the chain, and this chain cannot be altered. Now once some data is entered in the blockchain, we cannot remove that data. So every node will receive a copy of the updated chain. Talking of the blockchain architecture, this is how it looks. We have several blocks, and very importantly, how is this linked? Block N will be linked with a block. Have a look. Block N will be linked with block N plus 1. Block n plus 1 will be linked with block n plus 2. How? They are linked with the hash of the previous block. For example, block n is dependent on the hash of block n minus 1. N plus 1th block is dependent on hash of block n, and so on. So blockchain can be viewed as a log with records arranged in the form of time-stamped blocks. And all these blocks, what does it contain? It contains the hash value and the transactions. So many transactions are there. So we'll see in detail what these blocks actually contain. So, and we'll see how this linking is there. So for example, the first block, we call it a parent block or the genesis block. So we have some previous hash here, and we calculate the hash value. So how do we calculate the hash value? We'll see. So based on this data and the previous hash, we calculate the new hash. Now, in block 2, we have some other data, for example, Tuesday, and we take the value of previous hash to calculate the new hash. See, based on these two values, we have this new hash value. Similarly, this hash is taken by the block 2. So based on these two values, data Tuesday and the previous hash, we have this value. And again, based on the data, they have their own data, but they take the previous hash or hash value of the previous block. So we calculate this based on the values of these two. So what happens? If suppose you change somewhere here, for example, Monday, if you change this data, what will happen? This value will change because this data is changed. Now, if this is changed, it means this previous has this value will also change. And if the previous hash of block 2 is changed, it means this hash value calculated in block 2 is also changed. Similarly, this value is used in block 3. So if you change this this previous hash of block 3, again this value will be changed. So all the blocks are dependent on each other. Therefore, if the adversary, if the attacker, if the malicious user, if they want to compromise a blockchain, they have to change in all the blocks. If you change this Monday, you have to change this Tuesday also, Wednesday also, means you have to change data in all the blocks. However, this is never possible because this second point is very important, because complexity is increased to such an extent that till you tamper all the blocks, some new block will get added, and adversary never reaches the last block. So till you tamper all the blocks, some new block will get added, and adversary or the attacker will never reach the last block. So this is a general block architecture. Have a look. We have a hash value in block, and then we have nonce, timestamp, Merkle tree, root hash, and several transactions from transaction 1 to transaction n. We call it a block header and block body. Block body consists of transactions and the transaction counter. Counter is the number given to the transactions. And block header includes metadata such as nonce, n bit, timestamp, Merkle tree, root hash, parent block hash, and the block version. Metadata, data about the data about the transactions here. So transaction is nothing but a data structure that exemplify the transfer of digital assets among peers in a blockchain network. So transaction means the digital assets that you're transferring, that you're sending to some other. So moving on to the core components of a blockchain system, we have four things: asymmetric key cryptography, transactions, consensus, and blockchain. So we know what a blockchain is, we know what a consensus is, that is reaching to a common important term, asymmetric key cryptography, and how this is used in blockchain system. Cryptography plays a major role in securing data using blockchain. So we must know what is how this cryptography plays a major role in this blockchain technology. So use of cryptography in blockchain, see, at several, there are three different, you can classify the overall life cycle into three different phases. First, a transaction is initiated and broadcasted. See the blocks, three blocks you can see. First, initiation and broadcasting of transaction. Transaction is initiated, broadcasted to the network. Second, every node will validate the transaction. And once the transaction is validated, that needs is to be added to the block, and that block needs to be changed to the existing block. So these three stages, at these stages, use of cryptography is in the first and the last stage, especially. During initiation and broadcasting of transaction, we have the concept of digital consensus mechanism. There are n number of consensus mechanisms. For that matter, the most common consensus mechanism we have seen is POW, proof of work. We also have several other proof of authentication, POA, proof of capacity, PBFT, practical Byzantine fault tolerance. So there are n number of consensus mechanism. You can choose any one based on the requirement. And then for chaining of blocks, we have the hash function. So hash function, digital signatures, public key, private key, all these are some of the terms related to cryptography that are useful in this blockchain technology. We have been using this hash function, hash value so many times. So first of all, let's know what this hash function actually means. So in order to understand this hash function, we know this modulo operation, isn't it? Hash function is something that maps any size data to a fixed size. So for example, if you see this modulo operation, uh, if you have a value, suppose 2004, and if you apply 2004 modulo 5, what will be the value? We have the output as 4, the final value as 4. 2004 modulo 5 is 4. 24 modulo 5, the answer is 4. 204 modulo 5, the answer is 4. Whatever the value you give, whatever the size of data you give, the output comes to be a fixed size. So this is the first property of a hash value, and this property is actually fulfilled by this hash value, this modulo function. However, modulo, never confuse, modulo is not a hash function. Modulo only contributes to one half of the definition of a hash function, that modulo also maps any value, okay, to a fixed range, to a fixed size and within some range. So for example, suppose 29 modulo 5 will be 4, 27 modulo 5 will be 2. So this will be a fixed size, the output will be a fixed size of 1 and 1 bit, and it will be within a range 0 to n minus 1, means it will be within a range 0 to 4 if you use modulo 5. So whatever the value of x, if you use modulo 5, the answer will be within range 0 to n minus 1, that is 0 to 4. This is the first definition of hash function. Now, second one, for any two different x1 and x2, means for any two different numbers, x1 and x2, the hash, these two numbers should be different. Now, if moving on to the second part of the definition of the hash function, this modulo does not hold true, because if you have this modulo function does not satisfy the second definition of a hash value. If you have different numbers, the hash also should be different. And the major advantage of this hash value is it is a one-way function. Again, modulo will be able to fulfill this one-way function definition also. Have a look how. Suppose the output is 4 and the number is 5. Can you ever guess whether it was 24 or 204 or 2004 or 29 or whatever? It is a one-way function. If you are given 204, 29, 2004, whatever number, you can calculate, use modulo 5 and you can calculate the value. But if you are given a value between 0 to 4, will you be able to trace the original number on which the modulo 5 was applied? Never. So this is a one-way. This is one of the biggest advantage of the hash function. So modulo supports two things: maps a single any size data to a fixed size, and it is a one-way function. However, it fails to preserve the second definition of hash function, that for any two different x1 and x2, hx1 and hx2 should be different. So and also this is the how this hash and modulo is related. Further, cryptographically secure data also possesses something called avalanche effect. What does this mean? This means that even if there is a slight change in the input, even if there is a slight change in the input, the output changes drastically. There is a drastic or significant change in the output. So this is a avalanche effect, and cryptographically secure data have this kind of effect. So how do we calculate a hash? There are four things. Have a look: sequence number of the access, the client ID, the timestamp, and hash value of the previous hash. So how is H1 calculated? Have a look. We apply the hash function. Suppose here this hash function is a modulo function. So we apply this hash function over these four different items: client ID, sequence number of access, timestamp, and hash value of the previous. We calculate this hash. This is H1. Now, H2, the hash for the second block will be calculated using the same function applied over the same set of four items. The only thing is that this will use the hash of the previous block, and so on. So entire thing is hashed to connect it to the previous block. And if you make any change in H1, you need to change H2, you need to change H3, and you need to change all the blocks that we have seen. So this is how actually blocks in a blockchain are linked to each other with the help of a cryptographic hash function that makes it difficult to tamper. Properties of hash function: first one, collision free. If m1 and m2 is different, means if you have two different numbers, the hash value will be different. We know it is a one-way function, and very importantly, it is puzzle friendly. Means if you are given an output, you will not be able to trace back the input. For example, if this y is equal to hx and we apply this over k. So if you apply a hash value over any two terms, given the term that you use to divide, you will not be able to find the input. Given the output, you will never be able to trace the input. So this is very puzzle friendly. So these are some of the properties of the hash function. Moving on to digital signature, what it is, this is to verify the content of the document, identity of the sender, and prevent non-repudiation. Very important, non-repudiation in terms of computer security. If you have performed some transaction, you will never be allowed to refute from the claim of performing that particular transaction. That is non-repudiation. So we have rules to be followed here. So only the signing authority can sign a document, and everyone can verify the signature, and the signature is associated with a particular document. It is non-transfer. So we have the concept of encryption and decryption, symmetric key, asymmetric key cryptography. We all know what encryption is: converting plain text into ciphertext or readable format to unreadable format is encryption. And decryption, converting that same ciphertext, the message m dash, into this normal message is called decryption. We apply some algorithm. Now, why we have it here, why we have written it here? Because there are two types of cryptography: symmetric key, asymmetric key. Suppose we have converted this message m into m dash with the help of a key. If you use the same key to convert this m dash into m, we call it a symmetric key cryptography. If the same key is used for both encryption and decryption, we call it a symmetric key cryptography. However, if you use different keys for encryption, means if you convert this message m to m dash using one key, you need some other set of keys to convert this m dash to m. That is asymmetric key cryptography. So this is a major difference between symmetric and asymmetric key cryptography. So we have two types of key, means we need two different keys in this asymmetric key cryptography. One will be public key, other will be private key. It works under one rule: if a message is encrypted by a public key of one user, it will be decrypted by the private key of the same user. If it is encrypted by the public key of one user, it will be decrypted by the private key of the same user. So this is asymmetric key cryptography. Public key, private key, two types of keys. Public key known to everyone, and it is used to encrypt the message. Private key, personal, used to decrypt the message. So suppose Bharat wants to send a message to Bharat. So everyone have their private key. Bharat also have his private key. Bharti is also having his private key. Everyone sends up their private key in the public key in the pool. So Bharat knows the public key of Bharti. So what he will do, he have a message to send here. Suppose Bharat wants to send a message M. So he will use this message M and public key of Bharti, and on both these two things, message and the public key, he will use a encryption algorithm. So Bharat will use an encryption algorithm over the message and the public key of Bharti and convert this message into a ciphertext M dash. He sends this M dash to Bharti. Now, what will Bharti do? Bharti will decrypt the message with her private key, that is use this message M dash and the private key of Bharti, and use some kind of decryption algorithm here, and she will decrypt the message, original message. What happens here? If suppose there is some other user named Eve and Vector, if Bharat has encrypted the message with public key of Bharti, it will be decrypted only by the private key of Bharti. Even if Eve and Vector gets this message M dash, will he be able to decrypt the message M from this M dash? Never, because this message M dash can be decrypted into M only with the help of private key of Bharti, because this message was encrypted with the public key of Bharti. Therefore, who knows the private key of Bharti? Only Bharti, because here we can see public key known to all, private key is kept personal to decrypt the message. So even if other users, namely Eve or Vector, gets this message M dash, they will not be able to trace the original message. So it is only Bharti who will be able to read this particular message. So there is no point of confidentiality will not be lost. Nobody else will gain access to the sent message. We have a encryption algorithm, RSA, Ravish Samir Adleman algorithm, based on this name is given based on the scientist name Ravish Samir Adleman. These three persons actually coined this RSA algorithm that converts the plain text into ciphertext with the help of public key and ciphertext to the plain text with the help of a private key. So we have several steps here, so I'll not go into the details of this RSA algorithm at this point of time. So at the end of the day, at the end of the RSA algorithm, what we have, this is the algorithm. Okay. At the end of the algorithm, we have some kind of keys. Okay. This RSA algorithm generates the keys, and it will again keep the private key with the user, and it will announce the public key to all. So encryption will be done with the help of public key EN, and decryption will be done with the help of public key DN. So suppose what happens, Bharat will send a message M, and along with this message, he will also sign this message with his private key. So what happens here, the problem here was some in this, even though nobody else could access the message, the problem here was non-repudiation can be there. Suppose Bharat had sent a message to Bharti that please transfer $100 to Eve, I will send you later. And Bharti has transferred $100 to Eve, and Bharat, after she had sent, Bharat decides to refute the claim. I didn't send a message. Bharti will say, I had received a message. He will say that I don't know. I don't know who has sent it. I don't know. So I have not asked. So he can refute this claim of sending, of ordering Bharti to send $100. So this is non-repudiation. In order to overcome this problem, we have this concept of message sign or digital signature, you can say. We sign the message with the private key. So we send a message M dash, and also we calculate we have a sign. So Bharat sends the signature with his private, he signs his signature with his private key. So when this Bharti will decrypt his signature, she will find that this signature is encrypted by the private key of Bharat. Bharti can decrypt the signature, so it is signed by the private key of Bharat. It means it is Bharat who is only knowing the private key of his, and he is only the originator of this particular message. He cannot refute the claim of sending a particular message. Non-repudiation problem is solved. Have a look. So in order to reduce the signature size, we have a small signature for this. So we send a message and we also send a signature. We sign the message with this private key. So he has calculated a hash of the message, and he has signed this hash. Instead of signing the entire message, he's signing the hash. So Bharat generates the hash of the message M, HM, and So Bharat generates a hash of the message HM. He signs the message using his private key. Once he has signed it with a private key, it will be decrypted by his public key, and it will be clear that it is he who has sent a message. And he also sends the signature along with the message. Bharti will verify the signature using Bharat's public key, origin verified. Once the message is decrypted, once the signature is decrypted by the public key of Bharat, it means he has signed this message. So origin is verified. Second, she will compute the hash of the message received from Bharat and hash value of the message, and also she receives one hash from the signature. So once Bharti compares these two hash values, and if the two hash value is same, it means the message is not tampered. And if the two hash value is not same, it means the message has been tampered. So if the two hash value is same, it verified. In this way, blockchain actually verifies both the origin and the content of the message using concepts of cryptography. Talking of classification of blockchain, we have different types based on the permission. We have permissionless blockchain and permissioned blockchain. As the name suggests, in permissionless blockchain, we have any node can join or quit the network without any authorization. They need not submit their ID, password, or anything. They can join or quit the network, and nodes can use the common rules to receive, send, and validate the blocks. For example, Bitcoin. And in case of permissioned blockchain, before participation in the network operation, you need proper authorization. You need to undergo proper authorization, and therefore the effective network governance and identity revealing requirement is there. You need to reveal your identity before you participate in the network operation, before you enter into a blockchain. So this is used for internal business application. Further, you can also classify blockchain based on the participation. Either it can be a public blockchain, consortium blockchain, or it can be a private blockchain for that matter. Public blockchain is like participants can engage in the consensus process by reading and submitting the transactions if they are valid. And here some specialized nodes, like we said, some specialized nodes are called minor nodes. So whenever a set of transactions are broadcasted by the nodes, some request is made, some specialized nodes called miners, they actually collect these transactions to verify their validity, and the validity is validated, and they are formed in the form of a new block that is again added to the existing block. And then we have examples for this public blockchain is Bitcoin or Ethereum. Then we have consortium blockchain, where predefined set of nodes will control the consensus process. And this is partly private because some nodes actually control the consensus process. Example, a Hyperledger. Then we have private blockchain that keeps the read permission public, and write permissions is given to some particular nodes. So this is centralized to a single organization, the right permission. So one entity in a private blockchain rules the entire system. Nakamoto in his paper that was limited only to the money transactions. So it was enacted in Bitcoin cryptocurrency. After this first generation, we have the second generation that actually focused on assets or sales, where users can exchange numerous types of assets. Like it can be used for votes. We have seen e-voting systems being developed on the blockchain technology, and assets can be a goods, for example, in supply chain management, traceability of the goods in a supply chain management. So this was the second generation. Then we have the third generation that is actually related to the smart contracts that induced programmable contract named smart contracts that can be checked by all the participants. All the participants actually agree to some particular contract initially, and they are compelled to follow these contracts strictly. So this third generation significantly enhanced the blockchain capabilities, leading to its worldwide popularity. And popularity of blockchain, the adoption of blockchain cannot be debated at this point of time. There is huge growth in this blockchain technology. Ethereum have grown 50 times in the past few years. Talking of ICO investment, it again increased 16 times in the past 3 to 4 years only. The number of blockchain related job postings also, you can see it has tripled in the LinkedIn over the last year. So last year and this year compared, the number of jobs on the LinkedIn is also tripled. The amount of global blockchain market is expected to be worth $20 billion in 2024. So these are some huge numbers, and banks are currently experimenting with this blockchain technology. 69% of the banks are actually experimenting. Some have also adopted. Bankers are expecting commercial blockchain adoption over next year. So reported potential annual saving for banks utilizing blockchain is 8 to 12 billion US dollars. So this actually comments over the growth of this blockchain technology. Blockchain is something that can secure data, and that can enable you to actually share data amongst users securely in a secure manner. And today's IoT systems are actually, so much data is being generated by today's IoT systems, so these data needs to be safeguarded. So, and these IoT systems are lacking capability to defend themselves because of resource constrained nature. We have sensors. These sensors are energy constrained and resource constrained. So also some immature standards, resource diversity, absence of security mechanism for hardware and software design, deployment and development. So these are some of the reasons why this IoT is vulnerable. And blockchain has potential to upgrade the security features of this IoT. Being a centralized system, blockchain can enhance the security of this IoT and smart city. Papers that you can refer. These are some of my papers published in the last few years. First one was a blockchain for smart cities. All the three are detailed review articles. First one was blockchain for smart cities. And the second paper that you can see is a unification of blockchain and IoT. So both are in different directions. One is in the direction of smart city, one is blockchain for IoT. And third paper is untangling blockchain technology, will help you understand what are the different types of blockchain, what are the different application areas, how this blockchain can be useful for healthcare, for intelligent transportation systems, so on and so forth, how a transaction is realized. So if you want a detailed discussion or detailed analysis of what actually a blockchain is, go for the third one. And if you want a specialization key, blockchain for IoT, second one, and blockchain for smart city, the first paper. So these are the three works that I wanted to share with you all. My major research interests include wireless sensor networks, security in communication, Internet of Things, and blockchain and cryptocurrencies. Thank you. This is all from my end. Open for any kind of questions, please.
Thank you for so much for the detailed sessions. Just give me a moment. I'll unmute all the participants so that they can ask any queries if they have. Okay, participants, please ask your queries or any suggestions, sorry, any feedback, please feel free to give it right away.
Hello. Hello.
Yes, please.
Yeah. Can you explain about the job opportunities in blockchain?
Yes. See, currently most of these companies are actually Am I audible?
Yeah.
Yes. So currently most of the companies are looking for blockchain developers, and they are working on so many projects nowadays, especially suppose you work on this traceability in blockchain, traceability in supply chain, the banking operations. They are developing e-voting systems. So many applications that are dependent on this blockchain technology are being developed. So once you are able to work on any of these applications, so there are n number of job opportunities at this point of time. It is not at all limited to any one sector. So you cannot say it is limited only to the banking sector, or there are almost all the companies have started working on these different aspects. So you should be open to all these things. In LinkedIn also, as I mentioned in my slides also, the number of job postings have increased tremendously in this in the past 1 or 2 years. So this should be open to all, right?
Thank you.
Sir, may I ask one question?
Please, please.
So what is the future of IoT in mechanical engineering, especially in green building?
Future of IoT in mechanical engineering, at this point of time, see, I'm not from the mechanical engineering background, but IoT is something that is automating things, isn't it? Now, mechanical engineering is also entering this automation. So IoT contributes toward this. If you consider the scenario of Industry 4.0, this IoT is and mechanical engineering both have contributed toward the Industry 4.0. So yes, they
Yes.
have enough potential at this point of
In refrigeration system also play important role.
time. I would not be able to comment on this refrigeration system.
Thank you, sir.
Yes.
Professor Nazir, do you want to ask a query? Sorry, I think it's Professor Nasser.
Okay. Okay.
Okay, any more queries? Sir, yes, sir, Rizwan, sir, please unmute and ask your query, sir. Rizwan,
I
sir?
think I think you can type the query in the message if there is some problem.
Hello.
Yes, yes, please, please.
Sir, I would like to know the programming part, that which programming languages are in general used to develop these type of hyperledgers and smart contracts. So
Okay.
we need to know any new programming language or Python and Java will be okay.
No, at this point of time, Python and Java is more than sufficient.
Okay, sir.
From my view, Python and Java is more than sufficient. Take anyone.
And which platform actually we use that, like,
Yes, sir.
is there any specific platform? Like for Java, NetBeans we use. So,
Java NetBeans is fine. I guess Java NetBeans is fine. You can use that. There's no
okay,
problem.
okay. Right.